Hello, everyone. My name is Alex Wilkie. I'm an emeritus professor at the University of Manchester in the UK, and also a visiting research fellow at the University of Oxford, which is where I'm physically located at the moment. And it's a great pleasure for me to introduce Lexing Ying, who's a professor of mathematics at Stanford University and also a member of the Institute for Computational and Mathematical Engineering. And he's going to talk to us today on Prony's method, analytic continuation, and quantum signal processing. Professor Ying.
Thank you, Professor Wilkie. And let me share my slides. Okay, can you see me, and you can see the slides, right? Hello, I just want to make
fine.
Yeah.
That's
okay,
fine.
Great.
Yeah.
Okay, great. Thank you very much. So today I'm going to talk about Prony's methods, analytic continuation, and quantum signal processing. Okay. So the talk has three parts. The first, I'm going to introduce what is the Prony's method, and then I will talk about the two applications, noisy analytic continuation and also quantum signal processing. Okay. So here's a problem statement for the Prony's to introduce the Prony's method. So let's consider a sum of Fourier modes with unknown frequencies and unknown weights. And here, D stands for the number of these frequencies, which is also unknown. And Wj, omega j are the frequencies, and Rj are the weights. Now the problem is that given the function fk at the integer values of k, what we're trying to do is that we're trying to find the number of the frequencies d, and also try to figure out these frequencies and also these weights. So this is a very common problem, and Prony's method is one way to a classical solution which developed probably about 200 years ago to solve this problem. Let me introduce this shorthand notation f sub k, which is function values of k, f at the integer values of k. And now to introduce the Prony's methods, let's try to take a look at these frequencies one by one. So we start by forming these vectors, e to the I omega j k, for different integer values of k. So you can think about this to be an infinite long vector. And we introduce a shifting operator s, which is a shifted the whole vector up one slot, okay, to upwards. So when we apply s to this vector, you see that essentially just can move every slot up every self by one slot. So in fact, every entry is going to be multiplied by e to the I omega j. So therefore, s minus e to the I omega j multiplied this vector is equal to 0. Okay, this is very important for us. And now let's take the product over all these terms, s minus e to the I omega j, and because one of them is going to kill this vector and make it 0, and so and all these terms commute with each other. So therefore, if you take the product and apply to this vector, it's also going to give you 0. Now, the key observation is that when you take the product, this whole product itself is is independent of this j now, right? So therefore, what we can do is that we can take the sum over all these j's with weighted with rj. So therefore, this term itself is also, this equation is also equal to 0. Now we observe that this is actually our fk, which is something that we have access to. So there's a product of this operator applied to this long vector fk is equal to 0. So this is what I'm summarizing here. Now let's introduce a polynomial, which is the product of s going from 1 to d and z minus e to the I omega s. Now we don't know this at d, we don't know omega s, but nevertheless we know they exist. So therefore we can reason about this polynomial. And let's denote by mz, and let's denote all the coefficients by m0, m1, and all the way to md. Okay. So therefore, this key equation that we just derived on the previous slides can be written as m as this polynomial applied to this shift operator s, and applied to this vector fk, which we have access to, is equal to 0. Now, this actually is very useful because once we try to expand this, what we see is that this is m0 times identity applied to this vector, and m1 apply s applied to this vector, and all the way to md s to the power d applied to this vector equal to 0. If we write down in terms of matrix notation, what we get is that these, which we get is this linear system. where the first column is all these integer values of f at the integer values, f which would put in the first column, and then we shift them one slot upwards, and we'll put in the second column, and so on and so forth. And at the end, we shift by these slots, and we'll put the last column. And this multiply these d plus one dimensional vector m0 to md is equal to 0. Now, by looking at this equation, we see that the rank of this matrix is actually is actually going to give us d, and the null space of this matrix, which is one-dimensional, is actually going to give us any non-zero vectors in the null space is going to give us coefficients m0 to md. Now, once we have this coefficients m0 to md, we can form this polynomial mz, and by finding the roots of the mz, it will give us these e to the I omega s, which are the frequencies we need. Okay. So once we figure out these frequencies, and we can solve this least square problem, and to figure out the weights Rj. Okay. Though this is a key idea of the Prony's methods. Now, there's a lot of application of the Prony's methods, and in signal processing and control and dynamic systems. And the main advantage of the Prony's methods is that the method is quite adaptive in the sense that it does not require these frequencies omega s, omega j's to live on any fixed grid. It allows you to identify these grids, identify these frequencies. And also it's quite direct because all we need is to rearrange this vector and also perform the calculation of the null space. And it's also quite fast. However, on the other hand, because it requires root finding, here this step, it's also sometimes it can be quite sensitive to noise. So therefore we have to apply carefully. Now, in the remaining of this talk, I will try to talk about the two recent applications I've been working on of the Prony's methods. And the first is the noisy analytic continuation, and the second is quantum signal processing. So let's start with the first application. So the analytic continuation problem, the general problem of analytic continuation is the following, is that given a function gz, its value on a set of points, and we're trying to find its value elsewhere in the complex plane. So this is a hard problem, and as we know, it's some of you might know it's quite ill-posed. So more specifically, we consider a slightly simple version of that, which is called pole identification. So we're going to consider analytic function gz, which is the sum of a bunch of poles, where the pole location is denoted by Cj, and the pole weights is denoted by Rj. And the number of poles d is unknown, but it's nevertheless we assume it to be small. And one more thing is that we assume the poles to be on the real axis and the weights Rj to be positive. So the particular form of this pole identification problem has a lot of applications in computational chemistry and the physics. Now, what is a computational problem? And the computational problem is the following: that given noisy values of this gz at a finite set of points, which here we consider the case of the fermionic Matsubara grid. So these are the points on the imaginary axis, and which is denoted by the blue dots in this figure here. So it's the spacing between any 2 points is equal to 2 pi over beta, and we consider a finite number of them ranging from minus bi to plus bi. And here the beta is something called the inverse temperature, which is 1 over T, the temperature. Now the goal is to find d, which is the number of poles. Here in this figure, there's 3 poles living on the real axis, and the location of the poles, which shows the Cj, and also the weights of the poles, which is Rj. Now, I'll make one assumption, which I will remove later on, is that we assume that these Cj's do not overlap, does not reside in the grid from minus epsilon to epsilon. So therefore, the support of the red line, which denotes the support, potential support of the poles, does not touch the origin. Okay. All right. So how do we solve this problem? Well, before I dive into the details, let me comment that this problem is actually quite different from the Prony's method that I discussed a few slides ago. The reason is the following: is that the Prony's method has a data values in space, right? But the basis function that we consider are the Fourier functions, so they live in the Fourier domain. So in the analytic continuation, in fact, both the data and also the basis function is the space. And so it looks quite different. Now, there has been a lot of work on this analytic continuation, the pole identification problems. So here I'm listing the reference which I collected, which appeared after around 2000. Before that, there's a lot of papers, and I apologize for the ones that I did not list here. It's simply a vast literature. Now, to apply the Prony methods to this pole identification problems, so the first step is that we need to build a good approximation for this function gz we're trying to identify on this interval from -bi to bi. So this is illustrated by this figure. From these blue points, which is on the imaginary axis, the spiral grid, we're trying to construct a good approximation on this blue interval from -bi to bi. So this is which will allow us to access the function value on this blue strip, anywhere on this blue strip. Now let me comment that this is by no means a trivial task because we have to do this carefully, and part of the reason is because this is you pose problems and the data come with noise. So building a good approximation is actually quite important. However, this is not directly related to the pruning methods I'm going to talk about, so I will just try to leave it as this at this point. Okay. Assuming we have the good approximation of gx on the imaginary strip, which from -bi to bi, we can perform analytic continuation. There's essentially two ways to do it. One way is what we typically find in most of the complex analysis textbooks, which essentially said that we're going to build local Taylor expansions and then try to patch the small disk one after another to go over the whole complex plane and try to see where the poles are. However, from a numerical point of view, this method is not going to be very stable. And in fact, any methods based on derivatives and differences are not going to be stable. But instead, what we're going to do is that we're going to take a much more stable approach, which is based on integrals and based on Cauchy integrals. And numerical is based on the trapezoidal quadrature. Okay. So the key step of doing it is this unzipping step. So what we're going to do is that we're going to unzip this strip, which along the imaginary axis, and we're going to tear it and make it into a circle. Okay. And this is performed. So on the left-hand side, we have the Z domain. On the right-hand side, we apply this unzipping. We have a warped complex plane, as we call it the T domain. And this unzipping procedure is given by this formula, very simple formula: Z is equal to B over 2 and T minus 1. Okay. So you see from this figure is that unzipping transform this this strip -bi to bi on the imaginary axis to this unit circle, and the domain outside the strip, the complement of this imaginary strip has been pushed outward, and these two the real axis remain to be real axis, and the poles also being pushed forward, pushed outward a little bit. Now, the important thing to realize is that this analytic transformation, conformal transformation. So therefore, the poles maps to poles. So the function gz, which is of this form, we're trying to of this form is transformed into a function gt, where the pose remains to be the pose, even though the weights can change, and potentially plus an extra analytic function. Okay. So the advantage of that is that if we want to find the pose in the z-plane, which is these CJs, we can in fact work with these the t-plane by trying to find out the tau j's first, and then apply the inverse of these conformal map to figure out what is this CJs. Okay. Now to find out this tau j's in the t-plane, what we do is that we consider the following integrals of the form 1 minus 2 pi I over integrated over gt over t to the power k dt over t on the unit disk. Well, the reason we consider these integrals is that it serves an important bridge which bring the poles to the data that we have. The first is that if you consider the cases where k is greater equal to 1, and I claim that these integrals give important information about the poles outside the disk, which are the red ones in this figure. And I will skip the details of the calculation here, but this is just a simple application of the Cauchy integral formula. And in fact, this is equal to the sum of all the poles outside the disk and with the weights wj and multiply by the pole location tau j to the power minus k plus 1. So on the other hand, these poles, these integrals are also related to the Fourier transform of the function g on the unit circle, which is on this blue circle here. And this can also be done by just reparameterize the disk with the angle and do a simple calculation, and you see that this integral is actually equal to g to the power k. G, the Fourier transform of g, the case Fourier transform of g. Okay, so now because we have access to the function value on this unit circle, so therefore this Fourier transform can be computed easily with a trapezoidal rule and a fast Fourier transform. So in summary, this integral on the one hand gives us the Fourier coefficients and the case Fourier coefficients of the function g restricted to the unit circle. Now, on the other hand, it gives us it can be written as a sum of the poles to a certain power. Now, with this transformation, we're able to use a Prony's methods. And again, let me highlight this important formula here. To use the Prony methods, what we're going to do is that we're going to define this vector called a g hat k plus. And these are really just the positive Fourier modes of my function restricted to the unit disk. And here I'm rewriting each term and applying this formula to all the cases where k going from 1 to 3 all the way to infinity. Now, to apply the Prony's method, we again consider each of this each of the tau j separately. So here we have the vector tau j to the minus 2, tau j to the minus 3. So we fix the j and consider each of these vectors. And using the observation we made at the beginning of the talk, this upward shift vector, when we apply this to this vector, upward shift operator, when we apply to this vector, in fact, it's just equal to the vector multiply tau j to the power minus 1. So therefore, the shift operator minus this tau j minus 1 applied to this vector is going to be equal to 0. And then we take the product of all these terms and take the product over all the potential poles outside the unit disk. And this is also 0 because all these terms s minus tau j minus 1 to the power minus 1, they commute with each other. And then finally, now once we take the product, again, this is independent of j, so therefore we can add all these vectors and multiply all these vectors by wj and then add them together, and that will give me my g hat j plus vector. Now, the important thing is that here the g hat plus vector is something that I can work with because these are the Fourier coefficients that I just computed. Now, following what we did for the Prony's method, we define this to be our polynomial mt because it's in the t-plane now, so I denote it by mt. And this final formula now just can be written as mt. So now ms, right? It's applied to the shift operator, applied to this g hat plus vector is equal to 0. Once we expand this, we see that we get the following linear system. Now, the beauty about this linear system is that it's a linear system about these coefficients m0 to md of these characteristic polynomial about these poles, and this matrix is really accessible because I can compute all the Fourier coefficients. So now, if you take a look at the rank of this matrix, this will automatically give us d, which how many poles you have outside this unit disk. And if you take a look at the null space, and this will give you the coefficients of the characteristic polynomial, which is introduced here, right? And by computing the roots, you will be able to access this tau j to the power minus 1, and then by taking the inverse, and this will give you the location of the tau j. Now, once we have the location of the tau j in the t-plane, and what we really care about is the location in the z-plane, because this is where the original problem is formulated. So in order to do that, that's very easy because we just need to apply this formula, this map, and this will give us a location of Cj in the z-plane. Now, once we know the location of the Cj, most of the problem or hard work has already been done. So all we have to do is just optimize for these positive residuals by solving this constrained least square problems. So here, because Zn is corresponding to the Matsubara grid, which is known, and the Cj is already calculated, so the only unknown quantity is Rj, which can be solved easily with complex optimization routines. Okay, so this is the whole algorithm. So let me show you one numerical example to show the robustness of this method. So here we consider the problem with inverse temperature beta equal to 100. So temperature is 0.01. And the number of Matsuburger grid we use is n is equal to 128. So we only have 128 Matsuburger grid points on the imaginary axis. Now, as I mentioned, there's this gap assumption we made about this support of the poles. So here in the first case, we choose a gap epsilon is equal to 0.1. And so the problem has 4 poles, and the red circle corresponding to the exact location and their weights, and the blue circle corresponding to the recovered values. And you see that, and here have 3 figures. The noise level is 10 to the minus 4, 10 to the minus 3, and 10 to the minus 2. As you see that in all 3 cases, we were able to recover these pole locations of magnitude quite accurately. But obviously as noise increase, you see that the error increases as well. Okay. And in the second example, we have the gap value equal to epsilon equal to 0.05. And again, we have 4 poles. But because the gap value is small, you see that the poles that are close to the origin get closer to the origin, and the problem becomes harder. So in this case, you see that as we increase the noise level, we essentially also get a quite robust result, even though again, the error start increasing between the recovered locations and also the true locations. Okay. Now I'd like to make one comment is that previously I made this assumption that there's a gap epsilon equal to 0. But however, what if there's no gap? Okay. So what this means is that potentially I'll be able to have a pole which is very close or even exactly at the origin on the real axis. So in this case, I will not be able to consider the strip of minus bi to bi because the functions can potentially fail to be analytic on this strip. But however, I mean, we all know that instead of working with a complex plane, we can work with a whole, we can compactify it and consider the Riemann sphere, right? So instead of consider the strip going through the origin, we can in fact consider the strip starting from this lowest Matsuburger group and go all the way into infinity and come back. Okay, we're going the other way around on the Riemann sphere. Okay, so the first step would be to construct approximation of my GZ function going from this the pi I over beta all the way into infinity and then going back to minus pi over beta. So then the next step will be try to unzip this this blue strip which goes going at infinity, and this is given by this analytic transformation. So what will happen here is that we're going to take this the blue strip which going from this point to infinity and coming back, and we're going to unzip it, and this actually become a big circle, and this blue points map to here, and when it go to infinity, it's going to go here and then come back and finally come back to itself. Okay, so what happens now is that the real axis is going to be pushed in, it's going to be inside the unit circle, and the poles are going to be pushed in as well. But however, I mean, there's a very simple analytic transformation between these two domains. So instead of working trying to find a CJ here, it's equivalent to find a tau j and then going back. Okay, so now we have the problem is that now we have the following problem is that we have a function which is the analytic inside this unit disk, and also the value is going to continues continues all the way to the boundary of the disk, and we're trying to figure out these tau j's inside the disk. And to do that, we can also use the Prony's method, and it's very similar to what I described in the case where epsilon there is a gap. The only difference is that instead of considering the poles outside the unit disk, now we need to consider the poles inside the unit disk. And the only difference in the algorithm is that instead of considering the positive Fourier modes, and now we have to consider the negative Fourier modes. Okay, so I will not go into the detail of that, but I'm just trying to show that whether there's a gap or no gap, this method works. Okay, so this is the first application I want to talk about, and now let me move to the second application, which is quantum signal processing. Okay, I'll probably spend about 10 minutes trying to introduce the background of this topic. So quantum computing has become a quite active topic in the past 10, 15 years. And the problem we're trying to consider is the following, is that, so in quantum computing, all operators are realized as unitary matrices. Okay, so this is because we're talking about Schrodinger equation, we're talking about quantum mechanics. But however, in many cases, if we want to apply to quantum computer to real applications, you need to work with, we need to work with operators which are non-unitary. So the simple example is, for example, the Hamiltonian of a quantum system. It's not necessary. It's most of the time it's not a unitary matrix. So given an n by n Hermitian matrix A, where the n is very large, right, and the operator, this operator A is 2 norm is less than 1. So the key question is that how do we represent A with about log number of qubits? Okay. So there have been several methods being proposed in the literature, but in the recent years, it has become clear that one very popular way to do that is something called block encoding. So essentially what it says is that instead of represent A, what we're going to do is that we're trying to embed A into a bigger matrix. So potentially 2 times larger or 4 times larger or 8 times larger. And we denote this larger matrix called UA. And this UA is a unitary matrix. But however, if you take a look at the 1, 1 block, the top left block of this matrix, it gives you A. Okay, so in some sense, A is embedded in this big unitary matrix. So that's why we need this assumption the norm of A is bounded by 1. If it's not bounded by 1, what we need to do typically is to rescale the matrix so that the norm is less than 1 and then embed it. Now, but on the other hand, once given A, we're not particularly interested in A itself, right? We often want to consider some function of this matrix. So here I'm listing a few examples. The first example is called a Hamiltonian simulation. Think about A to be Hamiltonian, then this FA is equal to e to the power I tau A is actually the evolution of the Schrodinger equation. So this is, for example, it's very important to doing a quantum simulation. And the second example is called filtering, where I'm only interested in, for example, try the projection of this function, this operator into a very small interval on the spectrum, which is denoted by the delta here. So here you can think about the function look like this, okay? And the next example is fx is equal to 1x. This, for example, is very useful in inverse, and this is a key quantity in this recent topic for the quantum machine learning. Is essentially it's trying to do the inverse of the matrices. The final example is the Ferrell-Clement-Dirac operator. Now, for any of these operators, the key thing that we care about is not, in fact, is FA, and by using the this method of block encoding, and FA itself can be embedded into a unitary matrix, which is a few times large. Now, so from a computational point of view, that if you want to, given an A, want to work with FA, the task we need to do is that we need to start from a block encoding of the matrix A, and to get a block encoding of this matrix FA. Okay. Now, this is the main task which I'm highlighting here, and so this is a topic of this called a quantum single value transformation, which is initiated by this paper by Lo and Chang, and also Gian and Al expanded the area and introduced most of the things I'm going to talk about on this and next slide. So the idea is the following: is that give me a function fx that I'm trying to perform this transformation, and we're going to split it into even part and odd part. Okay, and here, because of the function, the spectrum of A is bounded from -1 to 1, so we only need to consider this function on the interval from -1 to 1. Once we have the even and odd part, what we're going to do is that we're going to try to approximate the even part by an even degree polynomial, which is denoted by AE, and similarly odd part by an odd degree polynomial denoted by AO. And now for both AE and AO, what we're going to do is that we're going to build a following circuit where this part of the circuit is essentially is implementing UA. So this is the block encoding of the A matrix. And the only extra thing is that one more extra qubit and plus a bunch of these controlled phase rotations given by this angle phi 0 to phi d, which depend on this polynomial. Okay, so finding this angle phi 0 to phi d is a key here to implement each term. So once we have both AE and AO implemented, we can add them together. Okay. So the key question is that give me an a polynomial A. How do I find these rotation angles such that this circuit itself is going to implement FAE, for example? Okay. Well, in terms of the language of the SU2 matrices, this really become a harmonic analysis problem on SU2. So give a polynomial AX, which could be either AE or AU, which I described on the previous slides, and this polynomial has to be supported is supported on interval from -1 to 1, and it has degree d, and the parity of the d is parity of the function is mod d, d mod 2. So for example, if it's an even polynomial, it's even degree. If it's an even degree, then it's even polynomial. If it's odd degree, it's odd polynomial. And this is also the assumption that we inherited from the fact that the norm of A is actually bounded by 1. So the computational task is then to find a sequence of the so-called phase factors phi 0 to phi d, such that the phi 0 to phi d reproduce AX in the following sense: that AX is equal to the real part of a function Px, where the function Px is defined to be the 1-1 block of this 2x2 matrices, and the 2x2 matrix can be written as a product of these sequence of operators, where each of the term either involve these rotation angles and involve the x. Okay, and here the z and x are the standard Pauli matrices. So the z matrix and x matrix, and we don't need the y matrix here. So for the rest of the discussion, it's useful to introduce a few notations here. So here we say that AX, the polynomial that we're going to approximate, is already equal to the real part of this 1-1 block, which is P. And so it's useful to introduce actual name for the rest of these this P and R's. So for example, the imaginary part of P is going to be called CX, and the real part of R is going to be denoted by BX, and the imaginary part of R is going to be denoted by DX. Okay. All right. So, in fact, it's actually useful to, as you have seen, that most of this talk is related to complex variables. So therefore, in fact, it's actually useful to lift these functions to complex domain. So I will do that in 2 steps. So for any function defined on the real interval from -1 to 1, it's natural that we can lift this onto a function on the unit disk. So this is what I'm going to do here. So for any function fx, we can lift this function to the unit disk by defining ft to be equal to f of cosine t. Okay, where this is done for the first half of the unit circle from 0 to pi, and then we extend it to the other half of the circle in analytically. Okay, so let me just give you an example, 2 simplest example about what does this mean here. So if you give me a polynomial, fx is equal to x, and the natural extension of this is equal to cosine t. And if the function is equal to fx equal to square root of 1 minus x squared, and then the function, after you do the extension, it will give you the sine t. So you see that if I have a function of the form either x polynomials or polynomial multiply square root of 1 minus x squared, and the extension onto the unit circle will be triple polynomials. Now, in terms of this t variable, this operator that this 2x2 big matrix I introduced on the previous slide, in fact, it can be written in a much more compact way, because now we get rid of these arc cosines x, and now it becomes t now. Now, once we lift it down to the unit circle, we can in fact further lift it onto the whole complex plane, right? And there's nothing stopped us from doing that. So again, we're doing analytic continuation. So we're gonna for the same f, we're gonna define these Laurent polynomials, which fz, where on the unit circle it's just given by this ft function that we just obtained. Okay, and again, for these 2 examples, when ft is equal to cosine t, and the Laurent polynomial associated with it is fz is equal to z plus 1 over z over 2, and for ft is equal to sine t, and the fz is equal to z minus 1 over z divided by 2 pi. Okay, so you see that, I hope I convince you that once you have this nice function on the unit circle, on this interval from -1 to 1, I can get a Laurent polynomials on the whole complex plane. So if we perform this for a, b, c, d that I introduced on the previous slide, which these functions here, right? And I can talk about the complex version, az, bz, cz, and dz. Now, let's come back to our problem, which need to find these phase factors. So there are 2 approaches which has been proposed in the literature for the constructing these phase factors. One approach is called factorization approach. So in this approach, what we're going to do is, this approach has been pioneered by these 3 papers. So in this approach, what we're going to do is that, recall that we have this az, right? We have this a function. We're trying to find the phase factors. So what we do first is that we're going to choose a BZ and such that it has a right parity, and also a squared plus b squared is less than 1 on the unit circle. Okay. So the second step of the factorization approach is that we're going to form this polynomial, form this Laurent polynomial, 1 minus a squared minus b squared, and we compute its roots. In fact, its polynomial will have 2D roots inside the unit circle. Okay, let's denote by CJs. And then we form, the next step is to form this polynomial, Laurent polynomial z EZ, which is z to the power minus d multiply the characteristic of a polynomial of these roots inside the disk. Okay. And we can also compute this factor alpha, okay, based on A and B and C. Sorry, E, once we have the E ready. Now, once we have the E and alpha, and the C and D functions can be written down analytically by this formula. So there's a lot of algebra goes into the derivation of these formulas, which unfortunately I don't have time to go to. But the point I want to highlight is that this is a pretty mechanical procedure to compute, to lead you to the phase factors. Now, once we have the Z and the D, we can add this A, B, C, D, these 4 functions to get a PZ and RZ. And recall that our U is equal to what? U is equals to P, R, and R star and P star. Okay. So once we have this P function and an R function, and again, it's a non-trivial but pretty simple and routine algebraic step to extract the phase factors. Okay. So therefore, what's the point of the discussion on this slide is that I want to highlight it that the most important thing is actually to find this easy polynomial in this factorization approach. Once we have easy, everything else follows in a fairly routine way. Now, well, this approach in principle works well, but numerically that does face some difficulties. The part of the reason is that finding the roots is not stable. So it's essentially the step finding the roots of these for this Laurent polynomial 1 minus a squared minus b squared, and in fact it cannot be done in the double precision arithmetic. It has to be done in extended arithmetic. So these papers show that in fact you need big O d log d divided by epsilon, where d is the polynomial degree, and multiply log d divided by epsilon bits in order to carry it out. And so therefore, if you think about d is equal to like 10,000, and this you require 10,000 bits at least, okay, which is not, but typically double floating point is only have 64 bits. Okay. There's also another approach which is based on called optimization approach, and the idea is to forget about these complicated formulas, which directly is try to optimize the phase factors such that the real part of this 1,1 component of this big U, 2x2 matrix U, is going to match our polynomial A. Okay, this is a hard problem. It's because it's highly convex. But in these 2 papers, what they showed is that in fact, if you start from a good initial guess, you will actually lead to the right solution, or at least one correct solution. Empirically leads to the correct solution. And the one advantage of this optimization approach is that it can be done in double precision arithmetic. And these 2 papers also prove that under the assumption that the polynomial, the infinity norm of the polynomial is smaller than 1 over d. So, so here, I mean, the main contribution of the rest of the talk is try to, again, find the algorithm which based on this factorization approach and using the Prony's method. Now recall 2 slides ago I mentioned outline the Prony's method, and the key is that in this factorization approach is that we form this polynomial, Laurent polynomial 1 minus a squared b squared, and we find the 2D roots inside the unit disk, and then we form EZ, where a key part is a characteristic polynomial. Now the key idea is that, I mean, in fact, we only need a characteristic polynomial, this blue piece, right? So what if we can directly compute this EZ, i.e. this characteristic polynomial, directly from this Laurent polynomial without going through the roots, and then I will avoid the stability problem. I can use double precision arithmetic. And the second part is that we have to choose BZ in a way so that to guarantee this can be computed as stable. But now let's just first elaborate on the first idea. Now to make a connection with the Prony's method, instead of looking at this Laurent polynomial 1 minus a squared minus b squared, we take a look at the reciprocal. It's 1 over a squared 1 minus a squared minus b squared. Now, because once you take the reciprocal, the roots become the poles. So therefore, at least inside the unit disk, And this function have a pole expansion, where the poles are exactly CJ's corresponding roots of the original Laurent polynomial. Now, so therefore, the problem becomes that I have access to this function gz on the boundary of the unit disk, and I want to identify the pole locations, right? But in fact, I mean, in the Prony's method, we identify the pole locations through the characteristic polynomial. So therefore, in this application, when we only need the characteristic polynomial, we don't even need to go to the poles. We just need to stop after we find the characteristic polynomial. So, and again, to do that, we consider again these integrals, which I've seen a couple of times. And in this case, because we have the poles inside the unit disk, we consider the integrals with an exponent k, which is less than equal to -1. So in fact, by following this, the same discussion I had for the Prony's method and for the analytic continuation, you see that the negative Fourier modes is in fact can be linked with the sum of the powers of these poles inside the unit disk. And this is a key relationship I'm reproducing on this slide. And again, follow the same procedure. We can define this vector, which consists of the negative Fourier frequencies. And we know that they can be represented as a linear combination of the poles and to a certain degree. Okay, and the rest is by now is pretty routine that we introduce a shift operator. And if we apply it to each of these CJ vectors, we see that it's S minus CJ applied to each of this vector give you 0. So you take the product over all the possible poles inside the unit disk, and this will still be 0. And by taking the linear combination of these CJ vectors with the weights Wj, this is also equal to 0. But the key is that this thing here is we have access to it, because this corresponds to the Fourier transform of a function on the boundary of the circle, which we have access to, just equal to 1 over 1 minus a squared minus b squared. Now, by choosing the BZ randomly, we can ensure that all these roots are going to be disjoint, right? So therefore, we don't need to count the multiplicity, they're always equal to 1. And therefore, what we can do is that we can define this characteristic polynomial, okay? And once we define this characteristic polynomial, this formula here is nothing but this characteristic polynomial m applied to operator shift operator s applied to my negative Fourier modes vector is equal to 0. Okay, once you expand this, you get this linear system. From this linear system, we know that its rank is equal to 2D because this is already guaranteed in this quantum signal processing application. And all we need to do is we need to find out one vector in the null space, and this will give me the coefficients of my characteristic polynomial, mz. And if I multiply by z to the power d, I will have this easy polynomial. And from the easy polynomial, I'll be able to discover these, recover all these phase factors accurately. Now, one more comment is that we have to still guarantee that these, the null space can be discovered in a stable way. To do that, let's just take a look at what will happen. Let me just tell you the solution. We're going to choose the BTs to equal to sine dt plus some low order terms, which is smaller terms. To motivate this discussion, let's just take a look at the two choices. One is BT is equal to 0, and the other is BT is equal to this choice I proposed. In the case of the BT equal to 0, and here I'm plotting, this picture is supposed to tell you what this numerically this matrix look like. So in fact, when BT is equal to 0, and all the values of this matrix have the value which will stay around 0. Okay, so in fact, if you perform the singular value decomposition, you see that even though this matrix has a rank 2D, but numerically the singular value drops dramatically. So you have a numerical null space actually huge. But on the other hand, if I introduce this BT, choose this BT equal to sine dt, what happens is that it has a huge anti-diagonal along the of the matrix, and there's only one the null space is exactly equal to dimensionally equal to 1. Okay.
Sorry, Lexing, you have 1 minute left.
Okay, so let me just show you a few examples. I have 4 examples here, but let me try to go through quickly. The first example is Hamiltonian simulation, and in fact, this is the function I'm trying to approximate. So in the first figure, I showed you what are the polynomial approximation of this function, which both the real part and imaginary part. On the second picture, I showed you as the tau goes up, where larger tau corresponding to a large simulation time, and the degree of the polynomial go from 1,000 degrees to 5,000 degrees. And this picture shows the total amount of time we needed to compute these phase factors. And in most of the time, it was about hundreds of seconds. And finally, it shows you the error is everything is around 10 to minus 12. And the second example is eigenstate filtering, and this is the shape of the filtering function, which is trying to pick out the singular value eigenvalue at 0 at the origin, and this is the degree, time, and error. And again, you see that the error is around 10 to the minus 12. The next example is matrix inversion, and again, running time is around a few tens of seconds, and the error is about 10 to the minus 13. And finally, we have the Feynman-Dirac operator, and the error is also around the 10 to the minus 12. Okay, so this is the summary, and I talk about three things: Prony's methods, analytic continuation, and the quantum signal processing. And thank you very much for your attention.
Thank you very much indeed. Thank you. It was, as I said, it wasn't my subject, but I enjoyed the talk very, very much and got a lot out of it, actually. Yeah, thank you.
Thank you.
And we'll have to finish now. Thank you very much. And thank you everyone for attending.
Thank you very much for all your support. Wish you a nice day, and see you, Professor Wilkie, in the next session.